All right, folks, this is a video on terminal velocity and force diagrams. So we're going to start by reviewing the force diagram for free fall. And the reason it's called free fall is the object is free from all of the other forces except the force of the weight. So let's say that you dropped the object from rest from some initial height d, some arbitrary height, let's call that capital H. So you know the velocity will eventually be down, and you know the acceleration is negative 9.8 and it is constant. Okay, so in your notes, just a quick review, make a sketch of the object's position function. Remember what we did in the baseball lab a long time ago. Velocity function as a review of what we just started doing, so not really a review, and the acceleration function. All right, so let's start with the position function. Everything's functions of time is the theme for this unit. Okay, so x starts at some arbitrary height h, and it doesn't decrease towards the ground at a constant rate. It decreases, the height decreases faster and faster and faster. So that is half of a concave parabola because that part of the parabola is the vertex. Okay, and your y-intercept is h. All right, the velocity function, also time starts with v equals 0. We could have thrown it up, we could have thrown it down, but it started at rest because that's what we're going to do. We're going to jump out of the airplane from rest. So it starts at 0, and the slope is negative 9.8 because the slope is constant, because the acceleration is constant. And so the velocity is becoming more and more negative at a uniform rate. Remember that the t-axis is really the point that in time at which v equals 0. So you're moving away from v equals 0. The numbers are getting more and more negative at a constant rate. All right, and then the acceleration function's kind of boring, but it's good to remember if it's constant, it's a boring flat line. It's always negative 9.8 meters per second per second. Okay, so that's free fall. That's our reference. Now, we're going to revisit bungee jump, and the bungee jump person also had weight, but they had the upward force of the bungee, and the formula for the bungee was F equals K delta X, where I'm just going to say X, where X was the amount the bungee was stretched. So the reason I want to revisit this is that as the bungee got more and more stretched, the force from the bungee increased. Gravity stayed the same, and K stayed the same. Remember, that's how strong the spring is. We're going to revisit springs in this unit. X is a function. X is changing. All right, so remember at some point, these two equaled each other, which meant that for a split second, forces were balanced, so the acceleration was 0. But in the meantime, the bungee jumper had gained some speed, right? So they have inertia. They're going to pass through equilibrium at maximum speed, because beyond that point, K delta X is even bigger than the weight. Sorry, the weight should stay the same size. But now the velocity is down and the acceleration is up. So Before max speed, the velocity was down and A was down, speeding up. At max speed, A is 0. Beyond max speed, V and A have opposite sign, and so it's starting to slow down again. And then you have your turnaround right before the river, and then you head back up. Okay, so we did that. We did bungee jump, and the force diagram wasn't constant. So I had to say, what's the acceleration at this one point? Like, I had to tell you where the person was to find the acceleration because it wasn't constant. And that's why we did TME. That's why we solve these problems using TME, because we can do that. We could not have used the physics Sudoku. Okay, so you have seen something like this before. So we're going to see some of the stuff is similar, some of the stuff is not. All right, so there's going to be two forces, but instead of having the bungee force in gravity, we're going to have the force of air resistance. And if you think about sticking your hand out the car window, the faster your car is going, the greater the air resistance. That's why you get better gas mileage at lower speeds. But also you can imagine holding your hand out like this or holding the hand out flat. The surface area of your hand, like how many air molecules you're physically running into. And then also we're going to see the density of air. That's why I think there's more home runs hit in Denver, because the air is less dense. Okay, you don't have to memorize this. I just want you to start thinking about this so you have a visual of what's causing the air resistance. Okay, so if the object is falling, shocker, we always have weight. Okay, so that hasn't changed. But now I want you to imagine this object is hitting the air molecules. Okay, so it has a couple of different terms for this if you're doing physics problems from another textbook or in college. Some people call it a drag force. Sometimes in the books they say R for air resistance. Is one of two things. If it's equal to some constant, it's proportional to to the speed, because the faster you hit the air molecules, the more collisions per second you have, the bigger the force. Okay, so for tiny objects like dust particles, it's a function of how fast you're going. And C is a constant that incorporates a bunch of things I'm going to talk about in a second, but you don't need to, you can just think of it as a constant. Some problems will say the force of air resistance is a different constant times the velocity squared. Okay, in reality, both of these terms are there. This one dominates at low speeds with small surface area. This one dominates at high speeds. We're not going to go that deep, that complicated, but you need to look at the problem and decide this, if it's proportional velocity, we're going to do this together in class. That's a differential equation. This you cannot solve using a differential equation, so this is actually easier because you can't do the tricky calculus. Okay, but what I want everybody to know, whether you're taking the AP or not, is imagine that pink vector, just like the bungee jumper. Gravity's winning, right? So you're speeding, A and V are in the same direction. So you're speeding up. So you're hitting the air molecules faster. So the air resistance increases. Gravity's still winning, so you're still speeding up. And then air resistance gets, you're hitting the air molecules faster, and air resistance gets bigger. So the air resistance increases like the bungee jumper, but it increases because it's a function of how fast you're going, not how much the bungee is stretched. Okay, so for the bungee jumper, the bungee kept stretching, right? And K delta X kept getting bigger. That's the main difference. For the terminal velocity, at some point, air resistance is going to equal the weight. you're hitting the air molecules fast enough that these two forces are going to be balanced. That means acceleration is 0. And because acceleration is 0, the velocity isn't changing. So the air resistance isn't changing. And so for the bungee jumper, this vector got bigger, and the bungee jumper switched from speeding up to slowing down. Here, neither force changes anymore. Gravity's constant, air resistance constant because it can't change because you're not hitting air molecules faster. Neither force changes, so acceleration is 0 indefinitely, which means you have the same velocity for the termination of your trip, which is why it is called terminal velocity. Okay, you stop accelerating, which is good, because if rain didn't reach terminal velocity, and we'd have not just a tornado drill this Friday, we'd have rain drills every time it rained. I'm not kidding. It would be a bad thing. Okay, so that is the concept, the big picture concept behind terminal velocity. And then I realized, like, this is just another visual that helps you realize the weight is constant, whatever it is. When you first jump out of the airplane, you're not hitting air molecules. For an infinitesimal amount of time, the air resistance is 0. But then it gets bigger as the velocity increases, and at some point it is equal. Okay. Who has a greater terminal velocity? Heavier person, lighter person, or is it a trick question? And you have to assume they have the same surface area and they're jumping through the same density of air. Okay, heavier person, because it's going to take, you're going to have to hit molecules faster to balance the greater weight, if that makes sense. You don't, to balance 600 newtons, you need to hit the air molecules, again, assuming they have the same surface area, you only have to hit the air molecules with a given speed. If this person has a weight of 900 newtons, you are going to have to hit the same number of air molecules at a greater rate in order for these two forces to balance. Okay, and then super quickly, I would try to keep the video short. Okay, how do you know it's a terminal velocity problem for people taking the AP? Do not just assume it's somebody jumping out of an airplane. Sometimes it's a car. It's all kinds of things, but the force is a function of velocity as opposed to x. So spring, the force is a function of x. Force is a function of velocity. Some terminal velocity involves integrating, and we're going to do that in class. And again, take more notes if you want, if you're taking the AP, but we're going to be careful about our upper and lower limits. We'll do that together. You can only do the tricky integrals if the air resistance is proportional to speed. So we actually prefer that the problems mean that the air resistance is proportional to speed squared, because it's an easy problem, which we're going to do in a second. Okay, so we're going to actually calculate the terminal velocity of a baseball given all of this information. This is the formula for the force of air resistance. Just want to talk about the terms. You don't have to memorize this. This is not a given equation. They'll just give you the combination of all this. Okay, rho is the density of air. That should make sense, right? If the air is more dense, you're going to collide with more molecules. C is the cross-sectional area of the object. If you going to hit more air molecules because you have a bigger cross-section. A is cross-sectional area, my bad. The drag coefficient is this C, because super quickly the semi-trucks used to look like this, and you can see the cross-section would be, this plus this, and then they added this kind of this domey thingy so that the air could flow over it easier. You have not changed the cross-sectional area, but you have reduced your drag coefficient. Okay, so that's what the C is in there. And then this is velocity squared. Again, you don't have to know any of this. I just want you to think about it so you can visualize what's going on. Okay, so full disclosure, I just typed into ChatGPT like terminal velocity of baseball, and it gave me this information. So that's where I got these values from. I assume they are correct. So I just plugged everything there into all of these terms, and I got 0.00129 v squared. So again, if it was a more humid day, or we went to high altitudes or something, that would be different. Blah blah blah. That's where I got all that stuff from. So that is all of that stuff together. Okay, so then I copied this so we can do this problem. So it looks really complicated, but what does terminal velocity mean? Terminal velocity means I have the weight, and that air resistance vector has increased as the speed increased until they're equal. Okay, so I know how to calculate mg. The weight of the baseball is 1.421 newtons. The air resistance is 0.00129 v squared. As v goes up, air resistance goes up. At some point, they are equal. So the sum of the forces is 0, and let's make a positive. So we get 0.00129 v squared minus the weight equals 0. So you get v squared equals 1102. Take the square root of that. 33.2 meters per second, or about 70 miles per hour. So again, here is where I got my information from. If I can move this screen. So that's where I got it from, 33.1 or 74 miles an hour. So if you dropped a baseball out of an airplane, that is how fast it would be going. All right, that is terminal velocity, getting you to think about what it means, what causes it, and how to draw the force diagram so that we can focus on the graphs together in class. Thank you for listening.